Detecting alien megastructures around distant stars is a fascinating subject that draws on astronomy, engineering, and imagination. Researchers have been exploring various methods to identify these potential signs of extraterrestrial civilizations, using advanced technologies and telescopes that can capture light across vast distances. One of the most talked about methods involves monitoring star brightness, looking for unusual dips that could indicate the presence of large objects orbiting a star. For example, the Kepler Space Telescope, which has been incredibly successful in finding exoplanets, also observed the star Kik 8,462,852, which showed some irregular dimming patterns, leading to speculation about the existence of an artificial structure or possibly a swarm of comets. Scientists have also turned to radio signals, scanning the skies for any unusual transmissions that might suggest intelligent life. The search for extraterrestrial intelligence, or SETI, employs powerful radio telescopes to listen for signals that could be produced by advanced civilizations. These efforts have not yet yielded definitive evidence of alien life, but they continue to fuel our curiosity as we ponder the possibilities that might exist beyond our planet. Moreover, the idea of Dyson spheres, hypothetical structures that could wrap around a star to capture its energy, has captured the imagination of many. Such megastructures would theoretically emit waste heat that could be detected by infrared telescopes. The James Webb Space Telescope, which is set to provide unprecedented views of the universe, may offer insights into the thermal signatures of distant stars, allowing astronomers to search for signs of these massive constructs. It's also important to consider the role of citizen science in this field. Enthusiasts and amateur astronomers are increasingly contributing to the search for alien megastructures. Analyzing light curves and data sets from various telescopes, platforms that allow the public to participate in data analysis have opened new avenues for discovery, making it possible for anyone interested to contribute to the scientific process. As we explore more distant galaxies, we also gain insights into the types of stars that might support alien megastructures. For instance, stars like red dwarfs, which are the most common type in our galaxy, might host planets in their habitable zones. And the potential for life around these stars is a subject of ongoing research. In recent years, the discovery of exoplanets in the habitable zones of their stars has increased interest in the search for extraterrestrial life. These planets, located at the right distance to possibly support liquid alien megastructures, a captivating topic in the realm of astrophysics, refer to hypothetical large-scale constructions created by extraterrestrial civilizations designed to harness or manipulate energy, resources, or even entire stars. These structures are not just the stuff of science fiction. They arise from the investigation of unusual astronomical phenomena that challenge our understanding of natural processes in the universe. For instance, one of the most discussed candidates for an alien megastructure is the star Kik 8,462,852, also known as Tabby's star. Observations of this star revealed irregular dimming patterns, leading some scientists to speculate that a massive object, potentially an artificial structure, could be orbiting it, blocking its light. This idea gained traction because the light fluctuations were unlike anything seen in typical stellar behavior, raising the intriguing possibility that advanced civilizations might build vast constructs around stars, such as Dyson spheres, which are theoretical megastructures that could encompass a star to capture its energy. In astrophysics, the definition of alien megastructures often hinges on the scale and complexity of the structures in question, suggesting that they would be far beyond our current technological capabilities. Researchers look for signs of these structures by analyzing the light curves of distant stars. searching for patterns that could indicate the presence of large artificial objects. Although many of the phenomena attributed to alien megastructures can usually be explained by natural occurrences, such as dust clouds or the presence of comets, the pursuit of understanding these anomalies pushes the boundaries of our knowledge. The fascination with alien megastructures lies not only in the potential for discovering intelligent life beyond Earth, but also in the implications such discoveries would have on our understanding of technology, civilization, and the universe itself. Astronomers use advanced telescopes and methods to study these unusual light patterns, employing spectroscopy, which allows them to analyze the composition of starlight and reveal the presence of elements that might indicate activity around a star that is not typical. As researchers delve deeper into the cosmos, their investigations into alien megastructures continue to inspire both scientific inquiry and the imagination of people everywhere, leading to exciting discussions about the possibilities that lie out there in the vastness of space. While the existence of these structures remains unproven, the quest to find evidence of intelligent life and the advanced technologies it could employ drives scientists to explore the universe with ever greater determination and curiosity. The fascination with alien megastructures, those colossal constructions purportedly built by extraterrestrial civilizations, has roots in several key historical events and discoveries that shaped our understanding of the universe and sparked our imagination. One of the pivotal moments was the development of radio telescopes in the 20th century, which allowed astronomers to listen for signals from distant stars, looking for signs of intelligent life beyond our planet. This technological advancement, particularly in the 1960s, led to the establishment of the Search for Extraterrestrial Intelligence, or SETI, which aimed to detect radio signals from alien civilizations, igniting public interest and scientific inquiry into the possibility of advanced life forms. In the early 1970s, the discovery of pulsars, rapidly rotating neutron stars emitting beams of radiation, added to this intrigue as some initially speculated that these signals could be evidence of alien technology. The events surrounding the launch of the Pioneer and Voyager missions, which sent spacecraft beyond our solar system, also captured the public's imagination, as they carried messages intended for any potential extraterrestrial life, showcasing humanity's desire to connect with the cosmos. The turning point came in 2015 with the discovery of an unusual star, KIC 8,462,852, also known as Tabby's star, which exhibited strange dimming patterns that scientists struggle to explain. Some researchers hypothesize that these fluctuations could be caused by massive structures, possibly built by advanced civilizations orbiting the star, leading to a surge of interest in the idea of alien megastructures. This star's peculiar behavior was such a mystery that it prompted serious scientific investigations and media discussions, fueling a public fascination with the possibility that we might not be alone in the universe. Moreover, the advent of powerful telescopes and advanced imaging techniques has allowed astronomers to observe distant exoplanets in unprecedented detail, revealing intriguing characteristics that might suggest the presence of artificial structures. The idea that intelligent life could manipulate their environment to such an extent has captured the imagination of both scientists and the general public, leading to increased interest in the search for signs of alien megastructures. Another significant historical event was the rise of popular culture's portrayal of aliens and advanced civilizations in movies and literature, which helped shape public perception and interest in the potential for extraterrestrial life. The success of films like Close Encounters of the Third Kind and series like Star Trek introduced concepts of interstellar travel and alien societies to a wide audience. The concept of extraterrestrial intelligence has undergone significant changes over time, reflecting advancements in science, technology, and our understanding of the universe. In ancient history, many cultures believed in the existence of celestial beings, often attributing them to gods or mythical creatures as they gazed up at the stars and pondered the mysteries of the night sky. The ancient Greeks, for example, contemplated the idea of life beyond Earth, with philosophers like Democritus suggesting that there were countless worlds populated by beings like us scattered throughout the cosmos. Fast forward to the Renaissance, when the invention of the telescope allowed astronomers like Galileo to explore the heavens more closely, planting the seeds for a more scientific approach to the search for life beyond our planet. The 19th century marked a pivotal moment in the evolution of this concept with the advent of Darwin's theory of evolution, which opened up new avenues for understanding life beyond Earth. The realization that life could adapt and thrive in vastly different environments fueled speculation about the nature of alien life. During this period, the possibility of life on Mars captured the public's imagination, especially with the discovery of canals by astronomer Giovanni Schiaparelli, which many believed were evidence of intelligent beings engineering their world. As we moved into the 20th century, the development of radio technology and the invention of radio telescopes brought a new dimension to the search for extraterrestrial intelligence. Scientists like Frank Drake proposed methods for detecting signals from other civilizations, leading to the famous Drake equation, which estimates the number of active communicative extraterrestrial civilizations in the Milky Way galaxy. The 1960S also saw the launch of the Search for Extraterrestrial Intelligence, or SETI programs. They aim to listen for signals from distant worlds, igniting further interest and debate about whether we are alone in the universe. The concept of extraterrestrial life took a more serious turn with the discovery of extremophiles on Earth, organisms that thrive in extreme environments, such as deep sea vents and acidic lakes. This finding suggested that life could exist in places previously thought uninhabitable, expanding our understanding of where to look for aliens. The exploration of Mars and the icy moons of Jupiter and Saturn, like Europa and Enceladus, has only intensified these discussions, as scientists speculate about the potential for microbial life in subsurface oceans. Meanwhile, popular culture has played a significant role in shaping public perception of extraterrestrial intelligence. From classical in the vast realm of theoretical astrophysics, the concept of alien megastructures excites both scientists and enthusiasts alike, as these structures represent the extraordinary possibilities of advanced civilizations beyond our own. One of the most discussed examples is the Dyson sphere, a hypothetical construct proposed by physicist Freeman Dyson in 1960. This megastructure is envisioned as a vast array of solar panels or habitats orbiting a star, capturing a significant portion of its energy output. The idea behind the Dyson sphere is that a technologically advanced civilization would require immense energy resources, far beyond what could be harnessed from a single planet. By enveloping their star with this structure, they could potentially utilize nearly all the star's energy, allowing for incredible advancements in technology and lifestyle. Transitioning from the Dyson sphere, we come to the Alderson disk, another fascinating theoretical structure proposed by physicist Robert Alderson in 1978. This disk would consist of a massive flat disk surrounding a star, with a thickness sufficient to support life and ecosystems on its surface. The Alderson disk would be an immense feat of engineering, spanning millions of kilometers, and would provide a vast habitat for various forms of life, all while being able to harness the star's energy effectively. This concept sparks the imagination, as it suggests a world where entire civilizations could flourish on the surface of a disk, enjoying a stable climate and abundant resources. Beyond these two, there are even more ambitious ideas, such as the Niven ring, named after science fiction author Larry Niven. This structure would be a colossal ring encircling a star with a radius comparable to that of Earth's orbit around the sun. The Niven ring would provide a habitable surface area much greater than that of Earth, offering countless opportunities for life to thrive. The concept combines elements of engineering and creative storytelling, highlighting how fiction can inspire scientific thought. Another intriguing proposal is the Matryoshka brain, a theoretical construct that involves layers of Dyson spheres, each one encasing the previous layer, all designed to maximize computational power. This megastructure would be a massive computer, capable of simulating entire universes or performing calculations at unprecedented scales, reflecting the potential of a civilization that has reached an extraordinary level of technological advancement. Additionally, there is the concept of the Shkadov thruster, a proposed method of stellar propulsion that involves constructing a reflective structure around a star, which could redirect some of its energy outward. This structure could theoretically. Scientists are intrigued by the idea of megastructures, large-scale constructions that could potentially be built by advanced civilizations for several compelling reasons. One key factor is the search for extraterrestrial intelligence, often abbreviated as SETI, which has led researchers to explore how civilizations beyond our planet might harness energy and resources in ways that far exceed our current capabilities. The concept of a Dyson sphere, for instance, is a theoretical megastructure that an advanced civilization could construct around its star to capture a significant portion of its energy output. This idea is rooted in the observations of energy consumption patterns in our universe, where it is believed that any civilization capable of significant technological advancement would require immense energy to sustain its growth and development. Moreover, scientists have noticed unusual stellar phenomena that could indicate the presence of such mega structures. But for example, when observing some distant stars, researchers have detected irregular dimming patterns that cannot be easily explained by natural processes, such as planets or dust clouds obstructing the light. This led to speculation that these stars might be surrounded by artificial structures potentially built by intelligent beings. The Kepler Space Telescope, which has discovered thousands of exoplanets, has also contributed to this fascination, as the hunt for Earth-like planets in habitable zones continues to fuel our imagination about what advanced civilizations might achieve. Additionally, the vastness of the universe, with billions of galaxies and countless planets, raises the possibility that intelligent life could develop on a cosmic scale, resulting in civilizations that are millions, if not billions of years ahead of us. Such civilizations might possess technologies and capabilities that are beyond our current understanding, allowing them to manipulate their environments in ways we can only dream of. This idea is supported by the Fermi paradox, which questions why, given the vast number of stars and planets, we have not yet encountered any signs of intelligent life. One possible explanation is that advanced civilizations might be using megastructures or energy harvesting methods that are undetectable with our current technology. Researchers are also exploring the implications of our own advancements in engineering and construction. As humanity progresses, we are beginning to understand the feasibility of building large-scale structures such as space elevators or orbital habitats. This reflection on our own potential has led scientists to entertain the idea that other civilizations might have already developed similar or even more advanced technologies. The excitement around this topic is fueled by the idea that we may one day discover evidence of these megastructures, providing a glimpse into the astronauts. Astronomers have developed a variety of innovative methods to observe distant stars and their environments, utilizing advanced technology and scientific principles. One of the primary tools in their arsenal is the telescope, which comes in many forms, including optical telescopes, radio telescopes, and space-based telescopes. Optical telescopes, which gather visible light, allow astronomers to see stars and other celestial objects, revealing important information about their brightness, color, and distance. Radio telescopes, on the other hand, detect radio waves emitted by stars and galaxies, providing insights into phenomena that are invisible to the naked eye, such as cosmic microwave background radiation, which is the afterglow of the Big Bang. Space-based telescopes like the Hubble Space Telescope are positioned beyond Earth's atmosphere, which can distort and absorb light. enabling clearer and more detailed observations of distant stars, galaxies, and other astronomical objects. In addition to telescopes, astronomers employ spectroscopy, a technique that involves analyzing the light emitted or absorbed by stars. By studying the spectrum of light, astronomers can determine the chemical composition, temperature, density, and motion of a star. This is possible because different elements absorb and emit light at specific wavelengths, creating a unique fingerprint that reveals the star's makeup. Another significant method used is photometry, which measures the intensity of light from stars over time. This technique helps astronomers detect variations in brightness, which can indicate the presence of exoplanets or other celestial phenomena. Furthermore, astronomers often rely on astrometry, which involves precisely measuring the positions and movements of stars. By tracking these movements, astronomers can infer the gravitational influence of unseen objects, such as planets or even black holes that may be orbiting the stars. This method has been crucial for discovering exoplanets, as the gravitational pull of these planets can cause their parent stars to wobble slightly, a phenomenon that can be measured with great accuracy. Another exciting method is gravitational lensing, which occurs when a massive object, like a galaxy or cluster of galaxies, bends the light from a more distant star or galaxy. This effect amplifies and distorts the light, allowing astronomers to observe objects that would otherwise be too faint or far away to detect. Gravitational lensing not only helps in studying distant stars, but also provides insights into dark matter and the structure of the universe. Additionally, the use of space missions and robotic probes enhances our understanding of celestial environments. For instance, missions like the light curve of a star, which is essentially a graph that shows how the star's brightness changes over time, can provide crucial clues about the presence of potential megastructures, such as Dyson spheres or other large-scale constructions that might be built around a star. When astronomers observe a star, they typically expect its brightness to remain relatively stable. However, if the light curve shows unusual patterns, such as periodic dips or irregular fluctuations, it can suggest that something is obstructing the light from the star. These dips in brightness could indicate the presence of a planet or, in more speculative cases, a massive artificial structure. For instance, the discovery of Kik 8,462,852, often referred to as Tabby's star, presented a fascinating case. Its light curve exhibited dramatic and irregular dips in brightness that could not be easily explained by known planets or natural phenomena. Some scientists proposed that these anomalies could be caused by an enormous structure orbiting the star, possibly constructed by an advanced civilization. This idea gained attention because the light curve did not resemble the typical patterns associated with transiting planets or stellar activity, leading to discussions about the potential for extraterrestrial engineering on a grand scale. Moreover, the analysis of light curves allows astronomers to calculate the size, shape, and even the orbit of the object causing the dimming. If these objects are large enough to block a significant portion of the star's light, it raises intriguing questions about the capabilities of civilizations that might possess the technology to build such structures. The nature of the light curve, particularly its depth and regularity, provides insights into how often and how much light is blocked, which in turn helps astronomers to theorize about the characteristics of the potential megastructure. Additionally, researchers have been exploring other candidates with similarly peculiar light curves. The study of these patterns not only expands our understanding of the cosmos, but also fuels the ongoing conversation about the existence of intelligent life beyond Earth. As scientists continue to monitor and analyze the light curves of various stars, they remain vigilant for signs that could suggest the presence of these extraordinary constructions, which may offer a glimpse into the technological achievements of alien civilizations. This intersection of astrophysics and the search for extraterrestrial intelligence is an exciting frontier, one that continues to capture the imagination of both scientists and enthusiasts alike. The Kepler Space Telescope, launched by NASA in 2009, has played a crucial role in the search for alien megastructures, which are hypothetical constructions built by advanced extraterrestrial civilizations. Kepler's primary mission was to discover Earth-like planets orbiting other stars, and its innovative methods for detecting these planets have opened up new avenues for exploring the possibility of intelligent life beyond our own planet. By observing the brightness of stars, Kepler was able to identify periodic dips in light which indicated that a planet was passing in front of the star, a technique known as the transit method. This method not only helped in identifying thousands of exoplanets, but also in measuring their sizes and orbits, which led to the discovery of many planets within the habitable zone of their stars, where conditions might be right for life. Beyond just finding planets, the data collected by Kepler provided astronomers with insights into unusual stellar phenomena that could hint at advanced civilizations. For instance, some stars exhibited strange patterns of dimming that could not be easily explained by natural celestial events. One of the most famous examples is the star KIC, 8,462,852, often referred to as Tabby's star. Observations show that the star's light fluctuated in ways that scientists found puzzling. Some hypothesized that this strange dimming could be caused by a large structure, like a Dyson sphere, built by an advanced civilization to harness energy from the star. This idea sparked significant interest and debate within the scientific community, leading to more focused studies and observations using other telescopes to analyze the star further. Moreover, Kepler's findings have inspired the development of new technologies and methods to search for potential signs of alien technology. The telescope's data continues to be a rich resource for researchers, enabling them to refine models of stellar behavior and to explore the conditions that might allow for the existence of megastructures. As scientists sift through the vast amounts of data, they remain vigilant for anomalies that could indicate artificial constructs, thus expanding our understanding of the universe and the potential for life beyond Earth. Additionally, the legacy of Kepler has spurred interest in future missions designed to hunt for more evidence of extraterrestrial civilizations. Telescopes equipped with advanced imaging and spectral analysis capabilities aim to detect not only planets, but also possible signs of technology, such as artificial light or unusual atmospheric compositions that could indicate industrial activity. The search for alien megastructures, while still speculative, benefits greatly from the groundwork the mysterious light fluctuations of KIC 8,462,852, often referred to as Tabby's star, have sparked a surge of intrigue and curiosity among astronomers and space enthusiasts alike, igniting discussions about the possibility of advanced extraterrestrial civilizations. Discovered by the Kepler Space Telescope, Tabby's star exhibits irregular dimming patterns, unlike any observed in other stars, which typically show consistent brightness, or periodic eclipses caused by orbiting planets. The dramatic variations in light intensity led to numerous theories, ranging from the presence of a swarm of comets to the existence of a colossal artificial structure, sometimes whimsically dubbed a megastructure. This term refers to hypothetical constructs built by advanced civilizations, such as Dyson spheres, which are structures that could harness the energy of a star. The notion of megastructures, while still speculative, captured the imagination of both scientists and the public, leading to increased funding and interest in the search for extraterrestrial life. Researchers began to explore the implications of such discoveries, considering what it would mean for humanity's understanding of life beyond Earth, and fueling discussions about the technological capabilities of alien civilizations. Moreover, the unique characteristics of Tabby's star prompted scientists to examine other stars with similar light patterns, expanding the search for potential megastructures across the galaxy. This excitement has also inspired citizen science projects, inviting amateur astronomers to contribute to the monitoring of Tabby star and others, creating a collaborative effort to decode the cosmos mysteries. As discussions about Tabby's star continue, they remind us of the vastness of the universe and our ongoing quest to understand our place within it, encouraging exploration and fostering a sense of connection to the cosmos, prompting the question of whether we are alone in this expansive universe, or if we might one day uncover evidence of civilizations that have harnessed the very stars themselves. KIC 8,462,852, also known as Tabby's star, has captured the attention of astronomers and the public alike due to its peculiar light patterns, which some have suggested might be a sign of alien megastructures, but there are several alternative explanations for its unusual dimming. One prominent theory suggests that the star is surrounded by a large cloud of dust or debris, which could intermittently block its light, causing the observed variations in brightness. This dust could be the result of the star's own evolution as it ages and sheds material from its outer layers, or it could be remnants from a collision of celestial bodies, creating a dense field of particles that sporadically obscure the star's light. Another explanation is that the dimming might be due to the presence of a group of exoplanets, which could orbit the star in such a way that they transit or pass in front of it, blocking some of the light and creating the characteristic dips in brightness. The possibility of a swarm of comets is also considered, where a series of comets could be orbiting the star, with their orbits bringing them close enough to create temporary dimming events as they pass in front of the star. Moreover, some researchers have proposed that the star could be in a binary system, where another star's gravitational influence could be causing irregularities in the light output, leading to the observed dimming patterns. Additionally, changes in the star's internal processes, such as stellar pulsations or fluctuations in its outer layers, could also contribute to these variations, as stars are dynamic entities that can exhibit changes over time. Each of these explanations highlights the complexity of stellar behavior and emphasizes the need for further observations and research to better understand the true nature of KIC 8,462,852 as astronomers continue to gather data and refine their models to uncover the mysteries of this intriguing star, which remains an exciting area of study in the field of astrophysics. Scientists, in their quest to understand the universe, often find themselves pondering the nature of various astronomical observations, particularly when they encounter unusual structures or signals which may be indicative of either natural phenomena or potential alien megastructures. The differentiation process involves a careful and methodical approach, relying on a combination of observational data, established scientific principles, and extensive cross-referencing with known cosmic behaviors. Initially, astronomers gathered data using powerful telescopes, both ground-based and space-based, which capture a range of electromagnetic signals, from visible light to radio waves and even infrared emissions. When an unusual signal is detected, scientists first analyze its characteristics, such as its frequency, intensity, and periodicity. For instance, natural astronomical objects typically exhibit specific patterns, while signals that appear too regular or structured may raise suspicions of artificial origins. To further investigate, researchers compare the observed data with existing models of known celestial objects, such as stars, planets, and galaxies. They utilize computer simulations to recreate potential scenarios, which can help identify whether the observed phenomena align more closely with natural occurrences, like the transit of a planet across a star, or with the hypothetical presence of advanced technology, such as Dyson spheres or other megastructures designed to harness energy from stars. Moreover, scientists often consider the context of the observations, including the location in the sky, the object's distance from Earth, and its motion relative to other celestial bodies. By examining the surrounding environment, they can determine if the signals correspond with known cosmic events, like supernovae, pulsars, or cosmic dust clouds, which might explain the anomalous readings. For example, if a light curve shows variability that matches the known behavior of a pulsating star, the likelihood of it being an alien structure diminishes significantly. Pure collaboration plays a crucial role in this process, as scientists across the globe share their findings and insights, contributing to a more comprehensive understanding of the data. This collaborative effort not only enhances the robustness of the analysis, but also helps to eliminate biases that might arise from individual interpretations. In addition to observational data, scientists rely on theoretical frameworks and models developed through years of research. These frameworks provide a foundation for understanding the physical laws that govern the universe, including gravity, electromagnetism, and thermodynamics. By applying these principles, researchers can evaluate the feasibility of certain structures or phenomena, assessing whether they could exist without contradicting established science. Lastly, ongoing advancements in technology and research methodologies continually refine the ways In recent years, advancements in technology, particularly in the fields of astronomy and engineering, have significantly enhanced our capability to detect distant megastructures, those enigmatic constructs that might hint at advanced extraterrestrial civilizations. One of the most notable developments has been the improvement in telescope design, specifically the construction of larger, more sensitive telescopes, such as the Extremely Large Telescope, which is currently under construction in Chile. This telescope, with its advanced adaptive optics and enormous mirrors, will allow astronomers to observe faint light from distant objects, thereby increasing our ability to spot unusual structures that could indicate the presence of intelligent life. Additionally, the deployment of space-based telescopes, like the James Webb Space Telescope, has revolutionized our observational techniques. Unlike ground-based telescopes, which face issues like atmospheric interference, space telescopes can capture clearer images, allowing scientists to study the light emitted by far-off stars and planets more effectively. The James Webb, in particular, can detect infrared light, which is crucial for observing the heat signatures of structures that may not be visible in the optical spectrum. This capability opens new doors in the search for signs of megastructures, as it allows researchers to monitor exoplanets for artificial light or unusual heat patterns that could suggest the presence of advanced technology. Moreover, advancements in computer algorithms and in artificial intelligence have transformed data analysis in astronomy. These technologies can sift through vast amounts of data collected from observatories, identifying patterns that might go unnoticed by human observers. For example, machine learning algorithms can analyze light curves from stars to detect anomalies that could suggest the presence of megastructures, such as Dyson spheres, which are theoretical constructs built around stars to capture energy. These algorithms can also help in classifying and cataloging celestial objects, making it easier to focus on those that exhibit unusual characteristics. Another significant improvement has been the development of radio telescopes and their ability to detect signals from space. The Search for Extraterrestrial Intelligence, SETI projects, utilize these radio telescopes to listen for signals that may indicate the presence of intelligent life. Advances in radio technology have led to the construction of arrays like the Square Kilometer Array, which will be the largest and most sensitive radio telescope ever built. This array will enable us to scan vast areas of the sky for potential artificial signals, thus enhancing our ability to detect megastructures that may be transmitting electromagnetic waves. Furthermore, the evolution of imaging techniques such as interferometry has allowed astronomers to combine data. Spectroscopic analyses are incredibly valuable tools in the field of astrophysics, particularly when it comes to identifying the composition of potential megastructures, which are large-scale constructions that might exist beyond our planet, such as Dyson spheres or other hypothetical constructs created by advanced civilizations. This technique works by observing the light that objects emit, absorb, or reflect, allowing scientists to gain insights into their composition, temperature, density, mass, and even their motion. When light from a distant object passes through a prism, it breaks into various colors, creating a spectrum. And each element has a unique spectral fingerprint, which means that by studying the spectrum of light from a megastructure, researchers can determine what materials are present, as different elements and compounds absorb and emit light at specific wavelengths. For instance, if we were to detect a structure around a star, scientists would analyze the light that passes through or reflects off the structure. They would look for specific absorption or emission lines in the spectrum which correspond to the chemical elements that make up that structure. This process is similar to how we can identify the gases in a planet's atmosphere or the composition of distant galaxies. The presence of certain elements, such as carbon, oxygen, or metals, can suggest the construction materials of a megastructure. Moreover, spectroscopic techniques can also detect the thermal emissions from such structures, providing clues about their temperature and energy output, which could indicate their level of technological advancement. Additionally, by comparing the observed spectra with laboratory measurements of known substances, scientists can create models to help interpret the data, leading to more accurate conclusions about the nature of these megastructures. For example, if a potential Dyson sphere were constructed from solar panels, the spectrum would reveal information about the materials used in their fabrication, such as silicon or gallium arsenide. Furthermore, the spectral analysis can help determine if the structure is actively generating energy, as variations in the spectrum can indicate energy absorption or emissions that are characteristic of advanced technologies. In the search for extraterrestrial intelligence, these analyses are particularly crucial, as they could provide evidence of life or technological activity beyond Earth. Researchers utilize powerful telescopes equipped with spectrometers to observe distant stars and their environments, looking for anomalies or unusual patterns in the light spectra that could suggest the presence of artificial structure. Therefore, spectroscopic analyses not only help identify the composition of potential megastructures, but they also open up avenues for understanding the possibilities of life and technology in the habitable zone. Often referred to as the Goldilocks zone, is the region around a star where conditions might be just right for liquid water to exist on a planet's surface, which is essential for life as we know it. This zone is not too hot where water would evaporate and not too cold where it would freeze. Rather, it's just right, allowing for a stable environment where life could potentially thrive. In the context of searching for megastructures, which are vast constructions that could indicate highly advanced civilizations, the habitable zone plays a crucial role. Many scientists speculate that any intelligent life capable of building such megastructures would likely emerge on planets within this zone, as these planets would have the necessary conditions to develop and sustain complex ecosystems over billions of years. When astronomers look for signs of these remarkable structures, they often focus their efforts on stars that have planets located within their habitable zones. For instance, the search for Dyson spheres, hypothetical constructs that could surround a star to capture its energy, often centers on stars with known exoplanets in their habitable zones. The reasoning is straightforward. If a civilization were to harness energy on a massive scale, they would likely do so where the conditions are most favorable for life, thus making these areas prime targets in our search for extraterrestrial intelligence. Moreover, the significance of the habitable zone extends beyond just locating potential megastructures. It also helps scientists understand the distribution of life in the universe. By examining planets within these zones, researchers can assess the likelihood of life and the kinds of technologies that might evolve there. The presence of unusual signals, such as infrared emissions that cannot be easily explained by natural phenomena, could hint at the existence of advanced technology or megastructures, which leads to exciting discoveries. Additionally, the habitable zone is not a fixed boundary. It can shift based on various factors, such as the star's brightness and the planet's atmospheric conditions. This variability adds another layer of complexity to our search. For example, a planet with a thick atmosphere could support liquid water, even if it is slightly outside the traditional habitable zone. Thus, searching for megastructures involves considering a broader range of celestial bodies, not just those perfectly nestled within the habitable zone, but also those that may provide unique environments conducive to life and technology. As we explore the cosmos, the significance of the habitable zone cannot be underestimated. In astroengineering, a fascinating and ambitious field, refers to the theoretical engineering of large-scale structures that can influence or manipulate the environment in space. And in many ways, it ties closely to the idea of constructing megastructures. These megastructures, which can include anything from solar sails that harness sunlight for propulsion to Dyson spheres, which aim to capture the energy output of an entire star, require a profound understanding of astrophysics, material science, and engineering principles. The concept of astroengineering suggests that humanity could one day build these colossal structures not only to facilitate our exploration of the universe, but also to address pressing challenges on Earth. For example, constructing a space-based solar power station, a megastructure designed to collect solar energy in space and beam it back to Earth, could potentially provide a near-infinite source of clean energy, drastically reducing our reliance on fossil fuels. Astroengineering also opens the door to terraforming, which involves altering the environment of a planet or moon to make it habitable for humans. This could involve massive engineering projects, such as creating artificial atmospheres or establishing controlled ecosystems, which are themselves forms of megastructures. The challenges of astroengineering are immense, requiring advances in technology and materials that can withstand the harsh conditions of space, as well as innovative approaches to resource management. Since building these structures would likely require materials sourced from asteroids or other celestial bodies, rather than relying solely on Earth's resources. Moreover, astroengineering emphasizes the importance of sustainability, as any large-scale project in space must consider not only the immediate benefits, but also the long-term impact on both our planet and the cosmos. In this context, megastructures could also serve as a means to protect Earth from potential cosmic threats, such as asteroids, by creating a system of defense that could deflect or redirect hazardous objects. This intersection of astroengineering and megastructures thus highlights a vision for the future where humanity not only expands its reach into space, but does so in a way that is mindful of ecological balance and sustainability. In conclusion, as we explore the boundaries of what is possible with astroengineering, the dream of building megastructures becomes not just a matter of science fiction, but a tangible goal that could redefine our relationship with the universe, offering solutions to some of the most significant challenges we face on our home planet. The search for megastructures is considered a form of SETI, or the search for extraterrestrial intelligence, because it involves looking for large-scale constructions that could indicate the presence of advanced civilizations beyond our planet. The idea stems from the hypothesis that if intelligent life exists elsewhere in the universe, they might build massive structures for energy capture or other purposes, which could be detectable from Earth. For instance, one of the most famous candidates for such a search is the concept of Dyson spheres, named after the theoretical physicist Freeman Dyson, who proposed that a highly advanced civilization might surround a star with a shell or swarm of solar collecting satellites to harness its energy. This kind of megastructure would emit distinct signatures potentially observable through telescopes, such as unusual light patterns or infrared emissions, which would differ from natural celestial phenomena. In 2015, astronomers detected an unusual dip in brightness from a star known as KIC 8,462,852, or Tabby star, which sparked intense interest and speculation about the possibility of alien megastructures orbiting it, while further studies suggested that the dimming could be due to a cloud of dust or comets rather than extraterrestrial construction. The initial intrigue highlighted how the search for megastructures could overlap with the search for signs of intelligent life. The methods used in SETI often involve scanning the skies for radio signals or other forms of communication from extraterrestrial sources, but the detection of megastructures represents a different approach, focusing on the physical evidence of advanced technology. Moreover, the search for these structures encourages scientists to think creatively about what intelligent life might look like and how it could manifest in the universe. It prompts researchers to consider not just the biological aspects of life, but also the technological advancements that could arise from such civilizations. This multifaceted approach to understanding the cosmos can lead to new discoveries and a deeper understanding of our own planet's place within the vast universe. As we continue to develop our observational technologies, such as powerful telescopes and advanced imaging techniques, the potential to identify megastructures increases, making it an exciting avenue of exploration within the broader framework of astrobiology and the search for life beyond Earth. Researchers are increasingly harnessing the power of machine learning and artificial intelligence, or AI, to analyze vast amounts of astronomical data for the purpose of detecting megastructures, which are hypothetical constructions built by advanced civilizations, often speculated to be far beyond our current technological capabilities. One of the most well-known examples is the search for Dyson spheres, enormous structures that could potentially surround stars to capture their energy output. In the realm of astronomy, the data collected from telescopes is massive, comprising billions of data points, images, and spectra, which can overwhelm traditional analysis methods. This is where machine learning comes into play, as it allows scientists to sift through this overwhelming volume of information much more efficiently. Machine learning algorithms, particularly those involving deep learning, can be trained to recognize patterns and anomalies in the data that might indicate the existence of these megastructures. For instance, researchers might use neural networks which are designed to mimic the way the human brain processes information, to analyze light curves of stars. A light curve is a graph that shows the brightness of a star over time. If a megastructure, like a Dyson sphere, were to pass in front of a star, it would cause a temporary dip in the star's brightness, which could be detected in the light curve. By feeding these algorithms thousands of light curves, both with and without megastructure events, researchers can train them to identify the subtle yet significant differences between normal stellar behavior and that which might suggest an artificial object. Additionally, AI can assist in classifying and cataloging astronomical objects, helping to distinguish between natural phenomena and potential megastructures. For example, researchers at various institutions have employed machine learning techniques to analyze data from the Kepler Space Telescope, which has been instrumental in discovering exoplanets. By applying these advanced technologies, they can improve the accuracy of identifying unusual patterns that merit further investigation. Furthermore, AI can be used to analyze radio signals from space, distinguishing between natural cosmic sources and potential signals from extraterrestrial civilizations, which could also be indicative of megastructures. In this era of big data, the collaboration between astronomy and machine learning is blossoming, as researchers continue to refine their algorithms and models, ensuring they can detect the faintest hints of artificial megastructures among the background noise of the universe. The integration of AI not only enhances the efficiency of data analysis, but also opens new avenues for discovery, allowing scientists to focus on the most promising leads and reducing disorder in disorder. Astronomers encounter several limitations and challenges when it comes to detecting megastructures, which are hypothetical constructions on a colossal scale, such as Dyson spheres or other large-scale engineering projects associated with advanced extraterrestrial civilizations. One significant challenge is the vast distances involved in space, which can make it incredibly difficult to observe objects that are light years away. The light from these distant objects may take thousands or even millions of years to reach us, meaning that we often see them as they were in the past, not as they are now. This time delay complicates our understanding of the structure's current state and also limits our ability to analyze them effectively. Another limitation is the sensitivity and resolution of our telescopes. Current ground-based and space-based observatories have certain thresholds of sensitivity, which means they can only detect light or other signals above a specific energy level. Megastructures might not emit light in the same way as natural celestial bodies, or their signatures could be too faint for our instruments to pick up. Additionally, many megastructures could be designed to absorb or reflect light in ways that make them virtually invisible to our detection methods, which rely heavily on identifying energy signatures, such as infrared or visible light emissions. Interference from other celestial phenomena adds another layer of complexity. Stars, planets, and cosmic dust can obscure our view of potential megastructures, creating a noise that can drown out the very signals we seek. This interference can lead to misinterpretations or missed detections, making it challenging for astronomers to confirm the existence of such structures. Furthermore, distinguishing between natural and artificial sources of light is not always straightforward, which adds to the difficulty in identifying true megastructures among the myriad of celestial objects. Moreover, the theoretical nature of megastructures poses its own set of challenges. Since these constructs are largely speculative, astronomers must grapple with the limitations of current scientific understanding and models of astrophysics. They may lack definitive criteria for what constitutes a megastructure, leading to debates among scientists about what to look for and how to interpret their findings. Theories about the existence of advanced civilizations and their capabilities are often based on assumptions that may not hold true in reality, which can further complicate detection efforts. Lastly, funding and resources can also be a limiting factor in the search for megastructures. Observatories require substantial investment, and the focus of research funding often shifts towards more immediate or pragmatic scientific questions. The discovery of exoplanets, which are planets located outside our solar system, has significantly influenced the way scientists search for potential megastructures around distant stars. When astronomers identify exoplanets, they often focus on the conditions surrounding these celestial bodies, including the possibility that advanced civilizations might exist there. The search for megastructures, which could include things like Dyson spheres, hypothetical structures built by an advanced civilization to capture energy from their star, has gained momentum because of the insights gained from exoplanet research. As we discover more about the atmospheres, compositions, and orbits of these exoplanets, it helps to narrow down the stars that are worth investigating for signs of artificial structures. For example, if a planet is found within the habitable zone of its star, where conditions might be just right for life, astronomers might then turn their attention to that star to see if there are any unusual light patterns or other signs that could indicate the presence of megastructures. The Kepler Space Telescope, which has identified thousands of exoplanets, has provided a wealth of data that researchers analyze for anomalies that could suggest the existence of such advanced constructs. Moreover, the presence of exoplanets can affect how we interpret the light curves of stars. When a planet transits in front of its star, it can cause a temporary dimming, but if there are large artificial structures present, they might create different light patterns. Scientists are on the lookout for these irregularities, which could signal the presence of something built by intelligent beings. The search for megastructures is not just about looking for outright signs of life, but also about understanding the broader context in which these planets exist, including their potential for hosting civilizations capable of engineering massive structures. Additionally, the techniques developed for studying exoplanets, such as transit photometry and radial velocity measurements, have also been adapted to search for signs of megastructures. The methods are becoming increasingly sophisticated, allowing astronomers to detect even the slightest variations in light that could indicate something unusual. This cross-disciplinary approach, combining the study of planetary systems with the search for extraterrestrial intelligence, is creating new opportunities to explore the cosmos. As we continue to discover more exoplanets, our understanding of their environments expands, leading to more targeted searches for megastructures. The data collected from these distant worlds can potentially tell us about their atmospheres, chemical compositions, and even their potential for supporting the concept of alien megastructures, which refers to hypothetical large-scale constructions created by advanced extraterrestrial civilizations, raises intriguing possibilities regarding their influence on light and radiation emitted by their host stars. One of the most discussed ideas is the Dyson sphere, a theoretical structure that could encompass a star, capturing its energy for use by an advanced civilization. If such a structure were to exist, it could significantly alter the way we perceive the star's light, potentially blocking or redirecting a portion of the radiation that would typically reach us. This could result in a dimming effect where the star appears less bright than it should be, or the creation of unusual spectral signatures, which could be detected by our telescopes, indicating the presence of artificial materials or technologies. Another interesting aspect is the possibility of energy harvesting methods that might involve the construction of giant solar sails or reflective surfaces. These structures could reflect sunlight in different directions, creating variations in the brightness of the star as seen from Earth. Such fluctuations could be interpreted as potential signs of alien engineering, prompting astronomers to investigate further. Additionally, if an alien civilization is utilizing the energy produced by their star in a way that generates waste heat, this could lead to an increase in infrared radiation detected from the system, which might be distinguishable from the natural emissions of the star itself. Furthermore, the presence of megastructures could influence the stellar environment, including the formation of dust clouds or other materials that could absorb or scatter light. This could create a complex interaction between the star's emissions and the surrounding structures, leading to unique light patterns or even periodic dimming events. Observations of such phenomena could challenge our understanding of normal stellar behavior, prompting scientists to consider the possibility of intelligent design behind these changes. In some cases, if megastructures are built around a star, they could also impact the star's life cycle. For instance, if a civilization were to siphon off too much energy, it could theoretically affect the star's stability, potentially accelerating its evolution or altering its path. In the Hertzsprung-Russell diagram, which is a graph that categorizes stars based on their brightness and temperature, the implications of these megastructures extend beyond just the light we can see. They might also affect the types of radiation emitted by the star, including ultraviolet or X-ray emissions. If a civilization were to utilize advanced technology that interacts with these forms of radiation, it could result in detectable anomalies that would intrigue astrogravitational microlensing events occur when a massive object like a star or a black hole, passes in front of a more distant light source, such as a galaxy or another star, bending the light due to its gravitational field, which acts like a lens. This fascinating phenomenon not only illuminates the presence of dark matter, but it also opens windows into detecting potential megastructures, which are hypothetical constructions that could be immense in scale, like Dyson spheres built around stars to capture energy. When a gravitational microlensing event happens, the light from the background object may brighten and then fade, creating a temporary increase in brightness, which astronomers can observe and measure. If the light curve, this pattern of brightness over time, shows unusual features, such as multiple peaks, it may suggest the presence of more complex structures behind the lensing object. For example, if the light curve indicates an unexpected sharp increase in brightness, followed by a rapid decline, it may point towards the existence of a large spherical structure, as opposed to a simple star or planet, which would generally create a smoother light curve. Researchers have also suggested that if multiple images of the same distant object are seen, it could indicate that a massive structure is acting as a gravitational lens, possibly revealing more about what lies beyond our current observations. This is particularly intriguing because megastructures would require an immense amount of energy and resources, raising questions about the technological capabilities of advanced civilizations. Moreover, as we explore deeper into the universe, the study of these micro-lensing events could help us uncover whether such constructions could exist, or if they are merely the stuff of science fiction. Astrophysicists utilize telescopes that monitor light from distant stars to catch these fleeting microlensing events, and they analyze the data with the hope of discovering more about the nature of dark matter and the potential for extraterrestrial engineering. By observing gravitational microlensing, scientists can gather evidence that hints at the composition of the universe. And the more we learn, the more we can understand our place within it, while pondering the possibilities of what advanced civilizations might construct, if they exist, and how they may manipulate their environments. The exploration of advanced civilizations, particularly in the context of their engineering capabilities, can be analyzed through various theoretical frameworks, which provide insight into how such societies may function, innovate, and utilize technology. One significant framework is the Kardashev scale, proposed by the Russian astrophysicist Nikolai Kardashev in 1964. This scale categorizes civilizations based on their energy consumption and technological advancement, ranging from type 1 civilizations, which harness all available energy on their home planet, to type 2 civilizations that can utilize the total energy output of their star, and type 3 civilizations that can control energy on a galactic scale. This framework is not only useful for understanding energy management, but also for speculating on the engineering projects these civilizations might undertake, such as constructing Dyson spheres to capture stellar energy, or terraforming entire planets for habitation. Another important theoretical framework is the Fermi paradox, which questions why, given the vast number of stars and potentially habitable planets in the universe, we have not yet encountered evidence of advanced extraterrestrial civilizations. This paradox encourages us to consider the engineering capabilities that might be necessary for long-term space travel, colonization, and communication across vast distances, leading to discussions about the limitations and challenges advanced species may face, including resource depletion, societal collapse, or self-destruction due to technological overreach. Moreover, the concept of technological singularity, introduced by mathematician and computer scientist Vernor Vinge, suggests that once artificial intelligence surpasses human intelligence, it could lead to rapid advancements in technology and engineering that are beyond human comprehension. This raises questions about how an advanced civilization might manage such powerful technologies, ensuring that their engineering capabilities are used ethically and sustainably, and how they might solve complex problems that arise from their own creations. In addition, The evolutionary perspective on technology, as discussed by theorists like Joseph Needham and later by historians of technology, emphasizes how societies develop their engineering practices in response to environmental challenges and social needs. This perspective suggests that the engineering capabilities of advanced civilizations are not just a product of their technological resources, but also of their cultural, historical, and environmental context. For instance, the development of irrigation systems in ancient civilizations allowed for agricultural surpluses, which in turn supported larger populations and more complex societal structures, demonstrating how engineering is deeply intertwined with the evolution of civilization itself. Lastly, systems theory offers a framework to understand how various components of an advanced civilization, such as politics, economy, and technology, interact. And cultural perceptions of alien life significantly shape how scientists approach the idea of megastructures, which are hypothetical constructions that could be built by advanced extraterrestrial civilizations like Dyson spheres that could harness energy from stars or vast structures that might indicate the presence of intelligent life beyond our planet. Throughout history, various cultures have imagined alien life in different ways, from ancient mythologies that spoke of celestial beings to modern science fiction that portrays aliens as both benevolent and malevolent. And these narratives influence scientific inquiry by framing the questions researchers ask and the methods they use to explore the cosmos. For instance, during the Cold War, perceptions of potential alien threats prompted a surge in projects aimed at leasing out extraterrestrial intelligence, leading to initiatives like SETI, the Search for Extraterrestrial Intelligence, which thoughtfully scanned the skies for signals from advanced civilizations, driven by both hope and fear, rooted in cultural narratives about what alien life might mean for humanity. Moreover, the way we perceive aliens can impact the technologies we develop and the resources we allocate towards space exploration. Enthusiastic belief in the possibility of sophisticated extraterrestrial life can lead to increased funding for projects that aim to detect megastructures, such as those surrounding distant stars, while skepticism or a lack of cultural interest can result in those initiatives being underfunded or ignored. The media plays a crucial role in shaping these perceptions, as sensationalized stories about UFO sightings or alien encounters can spark public interest and consequently influence governmental priorities regarding space exploration and research funding. The fascination with megastructures, informed by both popular culture and scientific inquiry, leads to intriguing discussions within the scientific community, as researchers often find themselves balancing the excitement of potential discoveries with the need for rigorous empirical evidence. This interplay between cultural narratives and scientific exploration can foster collaboration among scientists, artists, and writers, creating a rich tapestry of ideas that propels inquiries into the possibilities of other life forms and their potential engineering feats. Additionally, cultural perspectives often dictate what scientists consider plausible, with some researchers advocating for open-mindedness regarding the designs and technologies that could exist beyond Earth, while others urge caution, warning against letting imagination overshadow scientific rigor. As societies evolve, so do their views on extraterrestrial life. And this evolution can lead to more nuanced approaches to the study of megastructures. For example, as our understanding of the universe deepens, cultural narratives shift, leading to a broader acceptance of the idea that life could take forms radically different from the search for extraterrestrial civilizations. Raises a multitude of ethical considerations as humanity stands at a crossroads, facing profound questions about our place in the universe and the implications of reaching out to potential alien life. First, there is the question of the potential impact on the civilizations we may contact. If we were to establish communication with an extraterrestrial society, we must consider the consequences of that interaction. Would we be imposing our values, our culture, and our understanding of life upon them? Or would we approach them with respect and an openness to learn? Moreover, there is the concern about the readiness of humanity to interact with an advanced civilization. Our technological capabilities, while impressive, may not reflect our moral and ethical maturity. Engaging with a more advanced civilization could bring unforeseen risks, such as the potential for exploitation or conflict. This leads to another vital consideration. Should we actively send messages into space, or should we adopt a more cautious approach, listening rather than broadcasting? The dilemma of whether to initiate contact or remain silent has been dubbed the Fermi paradox, which highlights the contrast between the vastness of the universe and the silence we observe. Additionally, there is the issue of protecting our own planet and its inhabitants. The potential for harmful consequences, whether through disease transmission, cultural disruption, or environmental impact, cannot be overlooked. We must ponder whether we have the right to endanger ourselves or other life forms by making contact. In this context, the principle of planetary protection becomes crucial, emphasizing the need to safeguard our biosphere while exploring the cosmos. There's also the moral responsibility we hold towards our fellow human beings. The pursuit of knowledge about extraterrestrial life should not divert attention or resources from pressing issues we face here on Earth, such as poverty, climate change, and social inequalities. We must ensure that our endeavors in searching for extraterrestrial intelligence do not come at the expense of addressing our own challenges. Furthermore, there is the philosophical question of what it means to be human in a universe that may be teeming with intelligent life. Contacting extraterrestrial civilizations could challenge our understanding of ourselves, our beliefs, and our place in the cosmos, prompting deeper reflections on existence, consciousness, and the nature of intelligence. Lastly, there is the intricate matter of consent. If we were to establish contact, how do we ensure that the beings we encounter can give informed consent to engage with us? This raises profound questions about communication, understanding, and the rights of non-human intelligences. The scientific community's response to claims of alien megastructures has been a mix of excitement and skepticism, reflecting a wide range of opinions and approaches to this intriguing topic. When reports first emerged, particularly with the observation of the star KIC 8,462,852, often referred to as Tabby's star, many scientists expressed genuine curiosity, as the unusual dimming patterns of the star could suggest something extraordinary. Perhaps even artificial structures designed by an advanced civilization. This kind of speculation, while thrilling, also prompted a careful examination of alternative explanations, such as the possibility of dust clouds or other natural phenomena that could account for the star's erratic brightness. Experts in astrobiology and astrophysics, drawing from extensive observations and data, have often emphasized the importance of rigorous scientific inquiry, suggesting that while the idea of alien megastructures is captivating, it must be approached with a critical mindset and a reliance on empirical evidence. Some researchers have even proposed that before jumping to conclusions about extraterrestrial engineering, it is essential to explore all conceivable natural explanations. As the universe is full of mysteries that often have explanations rooted in physics and chemistry rather than in alien technology. On the other hand, the excitement surrounding the possibility of discovering signs of intelligent life has led to serious research initiatives, including the Search for Extraterrestrial Intelligence, or SETI, which actively scans the cosmos for signals or signs of advanced civilizations. In this context, the notion of alien megastructures has not only inspired scientists, but has also sparked public interest and engagement in astrophysics as people become fascinated with the possibilities of life beyond Earth. However, skepticism remains a vital part of the scientific process, as many scientists warn against jumping to conclusions without solid evidence. They argue that extraordinary claims require extraordinary evidence. And until such evidence is presented, theories about alien megastructures should be viewed with caution. This tension between enthusiasm and skepticism is essential in the scientific discourse, as it drives researchers to pursue deeper investigations and more robust methodologies in their studies of the universe. Moreover, the dialogue surrounding such claims has encouraged collaboration across various scientific disciplines, leading to a more comprehensive understanding of astronomical phenomena. By combining the insights of astronomers, physicists, and even biologists, scientists are better equipped to analyze data and explore the underlying mechanisms of the universe. The interest in alien megastructures has not only advanced our understanding of specific stars, but has also contributed to the overall quest for knowledge about life in radio telescopes, those fascinating instruments that capture radio waves from space, play a crucial role in the ongoing search for signals from advanced civilizations beyond our own planet. These telescopes, often located in remote areas away from human-made radio interference, are designed to detect faint signals that may be emitted by extraterrestrial technologies. By scanning the cosmos, radio telescopes listen for specific frequencies that could indicate the presence of intelligent life. The search for extraterrestrial intelligence, or SETI, utilizing these powerful tools to sift through cosmic noise, looking for patterns or anomalies that stand out from the usual background radiation of the universe. The technology behind radio telescopes has advanced tremendously, allowing scientists to analyze vast amounts of data in real time. The vastness of space means that signals can be incredibly weak and far away. So these telescopes must be highly sensitive and capable of distinguishing between natural cosmic phenomena like pulsars and quasars and potential artificial signals. For instance, the Arecibo Observatory, before its collapse, was one of the most famous radio telescopes used in the search for alien signals. And it transmitted a powerful message in 1974 aimed at the globular star cluster M13 as a demonstration of human technological prowess and a beacon for any civilizations that might intercept it. Moreover, radio telescopes aren't just passive receivers, they are part of a broader network of observational strategies. Scientists often collaborate, sharing data from multiple observatories around the world, creating an extensive framework for monitoring the skies. One notable project, called the Breakthrough Listen Initiative, aims to survey the entire Milky Way galaxy and beyond for signs of intelligent life, using both existing radio telescopes and new technologies. This initiative underscores the importance of international cooperation in the quest to find extraterrestrial signals, as it combines the efforts of various institutions and researchers. Another fascinating aspect of radio telescopes is their ability to search for narrowband signals, which are considered more likely to be artificial in origin. These signals are distinct from the broad spectrum of natural cosmic background noise, making them a prime target for detection. In addition to looking for signals, researchers are also studying the potential for advanced civilizations to transmit intentional beacons or relay messages across vast distances, which could help guide our search. As we continue to explore our universe, the role of radio telescopes remains vital, not only in the search for extraterrestrial intelligence, but also in expanding our understanding of the cosmos. By listening to the whispers of the universe, the study of stellar evolution, which is the process by which stars change over time, offers fascinating insights into the potential for advanced civilizations to construct megastructures. As stars evolve, they go through various life stages, from their formation in stellar nurseries to their main sequence phase, where they spend most of their lives, and eventually to their stages, which can result in spectacular phenomena like supernovae or the creation of neutron stars and black holes. These stages are critical for understanding the availability and concentration of elements that are essential for building complex structures. When a star reaches the end of its life, particularly in the case of massive stars that explode as supernovae, they release a tremendous amount of energy and material into space. This material, rich in heavier elements like carbon, oxygen, and iron, becomes part of the interstellar medium, the gas and dust that exists in the space between stars. Over time, this material can coalesce to form new stars, planets, and potentially the building blocks of advanced civilizations. As we study how often stars go through these cycles, we can better understand where and when the necessary conditions for life and by extension megastructure construction might arise. Moreover, the life cycle of stars informs us about the habitable zones around them. For instance, stars like our Sun have a stable main sequence phase lasting billions of years, providing a long window for life to develop on surrounding planets. If a civilization were to develop on a planet in such a zone, they might eventually progress to the point of building megastructures such as Dyson spheres or Alderson disks, which are theoretical constructs that could harness the energy output of their star. Additionally, the study of exoplanets, or planets outside our solar system, is becoming increasingly important. By observing how stars evolve and their respective planetary systems, scientists can assess the likelihood of finding advanced life forms capable of constructing megastructures, the presence of certain elements, the stability of the star's output, and the age of the star system all play significant roles in determining how likely it is that intelligent life can arise and thrive. Furthermore, looking at the frequency of supernovae in various galaxies can reveal patterns about how often stars produce the necessary elements for life and technology. If we can determine that certain types of galaxies, particularly those that are rich in heavy elements and have stable star formations, are more conducive to life, then we can extrapolate the likelihood of the search for megastructures, those vast, often theoretical constructs that could exist in our universe, relies heavily on the collaboration between various scientific disciplines as it brings together diverse perspectives, methodologies, and expertise that are crucial for addressing the complexities of such grand concepts. Astrophysicists, for instance, study the physical properties of celestial objects, employing advanced technologies and techniques to explore distant stars and galaxies, while engineers contribute their knowledge of materials and structural integrity, crucial in theorizing how such megastructures might be built or how they could function without collapsing under their own weight. Moreover, astronomers play a vital role in observing and identifying potential megastructures, using telescopes that can detect light from billions of light years away, and they often collaborate with computer scientists who analyze the vast amounts of data collected, searching for patterns or anomalies that could suggest the presence of these massive constructs. Additionally, input from geologists and planetary scientists is essential as they understand the formation and evolution of planets and moons, providing insight into how megastructures might interact with their environments, including gravitational influences and geological stability. The field of biology also contributes, especially when considering the potential for life around such megastructures, as biologists study extremophiles and other life forms that could exist in harsh conditions, informing theories about how life might adapt or evolve in engineered habitats. Furthermore, a collaboration with sociologists and anthropologists can help hypothesize the societal implications of such structures, asking questions about how civilizations might organize themselves around these megastructures or how they might affect cultural development. The importance of interdisciplinary teamwork becomes even more evident when we look at the technological innovations required for detecting or even constructing megastructures. Physicists who delve into fundamental theories of energy and matter work hand in hand with chemists to understand the properties of new materials that could withstand the extreme conditions of outer space, or that could be used in constructing these giant structures. Each discipline adds a layer of understanding, creating a more comprehensive picture of what is possible. This collaborative approach not only enhances the depth of research and exploration, but also encourages innovative thinking as experts from different backgrounds challenge each other's assumptions and insights, leading to groundbreaking ideas and technologies that might not emerge from a single discipline alone. Thus, the quest for megastructures is not just a scientific endeavor, it is a tapestry woven from the threads of many fields, each contributing its unique colors and patterns. Future space missions could play a pivotal role in the search for alien megastructures, which are hypothetical constructs created by advanced extraterrestrial civilizations designed to harness energy or serve other monumental purposes. As technology advances, space telescopes like the James Webb Space Telescope will allow astronomers to observe distant stars and their surrounding environments with unprecedented clarity, enabling them to detect unusual light patterns or dimming events that suggest the presence of large-scale structures orbiting these stars. For example, if a star's brightness fluctuates in a pattern that cannot be explained by natural celestial phenomena, it may indicate the presence of a massive object or even an artificial construct obstructing or reflecting its light. Moreover, future missions could deploy specialized spacecraft equipped with advanced sensors to investigate these anomalies further, perhaps sending probes to study the materials and structures of these objects up close, if they exist. These missions might also analyze the chemical signatures of exoplanets in detail, looking for signs of industrial pollution or atmospheric changes that could hint at technological activity. Additionally, the search for alien megastructures may benefit from the development of new algorithms and machine learning techniques, which can sift through vast amounts of data collected by space observatories, identifying potential candidates for further study more efficiently than traditional methods. As we explore our solar system and beyond, missions to moons like Europa or Enceladus could also provide clues about extraterrestrial life and technology, as the presence of subsurface oceans raises the possibility of life forms developing advanced civilizations. Furthermore, these missions might help us understand the potential for future human colonization and the technology we would need to create our own megastructures. Understanding the energy needs of a civilization could guide our search. For instance, the search for Dyson spheres, theoretical constructs that could surround a star to capture its energy, would lead scientists to focus on stars with higher energy outputs and unusual patterns of energy consumption. In addition, as we gather more data from these missions, we might refine our definitions of what constitutes a megastructure, broadening the scope of our search to include more diverse possibilities. And the collaboration between international space agencies, universities, and private companies could drive innovative approaches to detect signs of alien engineering, creating a more robust framework for identifying potential megastructures. As we continue to push the boundaries of our understanding, the convergence of astrophysics, engineering, and data analysis will be crucial in unraveling the mysteries of the cosmos, keeping the dream alive that the potential discoveries that could fundamentally change our understanding of life in the universe, are vast and varied, often leading scientists and researchers to explore the very edges of our knowledge. One of the most exciting areas of exploration is the search for extraterrestrial life, which includes studying exoplanets, those planets outside our solar system. The discovery of a planet within the habitable zone of a star, where conditions might allow for liquid water, could suggest that life as we know it could exist elsewhere, perhaps in forms we have yet to imagine. For instance, the recent identification of Venus-like planets that have atmospheres rich in carbon dioxide also raises questions about the possibility of microbial life existing in the clouds of those planets, even if the surface conditions are hostile. Another potential breakthrough lies in the field of astrobiology, which examines the origins and evolution of life in extreme environments on Earth. Discovering extremophiles, organisms that thrive in conditions previously thought uninhabitable, such as the deep sea hydrothermal vents, acidic lakes, or even the icy surfaces of Antarctica, has expanded our understanding of the potential for life to exist in similar extreme environments elsewhere in the cosmos. If we find organisms that can survive in these harsh conditions on Earth, it provides a strong basis for the belief that life could exist on moons like Europa or Enceladus, where subsurface oceans may harbor life. The exploration of Mars also holds great promise, as ongoing missions are searching for evidence of past or present microbial life. If signs of ancient life, such as fossils or organic molecules, are discovered in Martian soil or rocks, it would not only reshape our understanding of life's history, but also suggest that life could have emerged independently on more than one planet. Such a discovery would imply that life is not an isolated phenomenon, but rather a common occurrence throughout the universe. Furthermore, advancements in technology, such as the James Webb Space Telescope, allow us to analyze the atmospheres of distant exoplanets for biosignatures, which are chemical indicators of life. The detection of gases like methane or oxygen in significant quantities, alongside the absence of other gases that would normally react with them, could indicate biological processes similar to those on Earth. This could lead to a paradigm shift in how we view life in its potential forms, as we begin to consider a broader array of possibilities beyond carbon-based life. Moreover, the concept of panspermia, the idea that life could be distributed throughout the universe via comets. When we think about the possibility of alien megastructures, we enter a fascinating realm of science and speculation, where the boundaries of our understanding of the universe stretch and bend. To define the criteria for potential evidence of such structures, scientists and astronomers rely on a variety of methods and observations which serve as the foundation for their investigations. Firstly, one of the primary indicators that researchers consider is unusual light patterns, which can indicate that an object is blocking light from a distant star in a way that cannot be explained by natural celestial bodies. For instance, the case of Kick, 8,462,852, often referred to as Tabby's star, raised eyebrows when it exhibited significant and irregular dimming, leading some to speculate about potential artificial constructs around it. Another important criterion is the size and scale of the observed phenomena. Megastructures, by their very definition, would need to be of immense proportions, often larger than any natural object we currently know. Astronomers look for anomalies that suggest engineering on a grand scale, such as a fleet of satellites or a Dyson sphere, which is a hypothetical megastructure that could encompass a star to capture its energy output. The distance from which we observe these anomalies also plays a crucial role. If the light patterns or structures are observed from vast distances, it's essential to consider how these objects could maintain their integrity over such expanses. In addition, researchers examine the spectrum of light emitted or absorbed by these potential structures. Different materials reflect and emit light differently, and by analyzing the light spectrum, scientists can discern whether the observed features align with natural compositions, or if they hint at artificial or engineered elements. This analysis can help distinguish between natural celestial phenomena, such as comets or asteroids, and something that might suggest the presence of intelligent design. Moreover, context is vital. The location of these anomalies is analyzed in relation to known exoplanets and star systems. A megastructure in a region that is rich in resources or around a star that exhibits unusual behavior could provide further evidence supporting the hypothesis of artificial construction. The search for extraterrestrial intelligence also involves listening for signals, which can be another criterion. If a megastructure is present, it might be accompanied by emissions that could indicate communication or energy use. Furthermore, collaboration among scientists, engineers, and theorists is crucial in this field. By pooling knowledge and expertise, researchers can develop more refined models to explain the data they observe, which can lead to Discovery of alien megastructures, which are vast artificial constructs built by extraterrestrial civilizations, could have profound implications for humanity, reaching far beyond the scientific community and into the very fabric of our society. Imagine if we were to find such evidence, perhaps through unusual light patterns or massive structures orbiting distant stars, it would challenge our understanding of life in the universe, leading to a paradigm shift in how we view our place in the cosmos. The existence of advanced civilizations might suggest that we are not alone, sparking a wave of curiosity, excitement, and even fear among people everywhere. As we grapple with this potential reality, we would likely see a surge in interest in space exploration, with more funding and resources directed towards studying the cosmos. Governments and private companies might accelerate their plans for missions to other planets and systems, hoping to uncover more about these civilizations and their creations. This could also ignite a new era of collaboration as nations come together, sharing technology and knowledge in the pursuit of understanding these megastructures. On a philosophical level, the implications could be staggering. If we discover that intelligent life has built enormous structures, we must confront questions about our own existence, our responsibilities as stewards of Earth, and the moral implications of reaching out to or interacting with other civilizations. The realization that we are just one of many intelligent species could alter our beliefs, challenge religious views, and inspire a sense of unity among humanity as we acknowledge a shared fate in a much larger universe. Furthermore, the technological advancements required to detect and study such megastructures could lead to innovations that benefit life on Earth. As we develop new tools and techniques to explore the cosmos, these technologies may find applications in various fields, from energy production to environmental conservation, potentially improving our quality of life and helping us address pressing issues like climate change and resource management. However, the discovery may also elicit anxiety and fear. The prospect of encountering a more advanced civilization raises concerns about the potential for conflict, exploitation, or even existential threats. The questions of whether these beings would be friendly or hostile could lead to a global debate about how to approach such a situation, emphasizing the need for careful planning and international dialogue to ensure that humanity responds wisely. In addition, the presence of alien megastructures could affect our scientific community, prompting new research in fields like astrophysics, engineering, and biology, as we seek to understand the materials and technologies that would allow for such grand constructions. Scientists use various methods to communicate their findings about megastructures to the public, ensuring that complex information is accessible and engaging. They often start by publishing their research in scientific journals, which are important for peer review and validation. But these articles can be difficult for the general public to understand. To bridge this gap, many researchers write summaries or articles for popular science magazines, blogs, or websites, where they can explain their findings in simpler terms. Additionally, scientists frequently participate in conferences and public talks where they can present their work visually using slides, videos, and even models, which helps to illustrate their points, making it easier for audiences to grasp the scale and implications of megastructures. Social media has also become a powerful tool for scientists to share their discoveries, with platforms like Twitter, Instagram, and YouTube allowing them to reach a wider audience through short videos, infographics, and engaging posts. Scientists can highlight the significance of their work and spark interest in megastructures. Many scientists collaborate with science communicators or journalists who help translate their findings into stories that are compelling and relatable, capturing the public's imagination and encouraging curiosity about the natural world. Moreover, educational outreach is another important avenue. Scientists often engage with schools and community organizations, conducting workshops or demonstrations that bring the concepts of megastructures to life for students and families. This hands-on approach not only educates, but also inspires the next generation to think critically about science and its impact on our understanding of the world around us. Documentaries and television programs produced in collaboration with scientists also play a significant role in communicating these discoveries, as they can visually represent megastructures in ways that are both informative and entertaining, allowing viewers to visualize the enormity and intricacies of these structures. In addition, podcasts have gained popularity as a medium for scientists to discuss their research in an informal setting, providing an opportunity for deep dives into specific topics while allowing for storytelling elements that captivate listeners. This format can make complex subjects more relatable and interesting, fostering a connection between scientists and the public. Overall, the combination of different communication strategies, peer-reviewed publications, popular media, social networks, educational outreach, and multimedia storytelling allows scientists to effectively convey their findings about megastructures, engaging the public's interest while also emphasizing the importance of understanding our planet's massive and often awe-inspiring creations. In the quest to understand the universe, some scientists have turned their attention to the possibility of alien megastructures, intriguing constructs that could signify advanced extraterrestrial civilizations. One of the most notable studies was published in 2015, led by a team of astronomers, including the renowned Jason Wright, who proposed that unusual dimming observed in the light from the star Kick, 8,462,852, also known as Tabby's star, could be the result of a large object or a series of objects blocking the starlight, rather than just natural phenomena like dust clouds or planets. This study sparked widespread interest and debate, leading to further observations and discussions about what such structures might indicate about the capabilities of extraterrestrial engineers, as well as the nature of stellar phenomena. Another significant paper, published in 2016 in the Astrophysical Journal, examined the possibility of Dyson spheres, a hypothetical megastructure that encircles a star to capture its energy output. The concept, first proposed by physicist Freeman Dyson in 1960, has led to various theoretical discussions about how such structures could be detected and what their signatures might look like when observed from Earth. The research emphasizes the technological advancements required for such a civilization to construct and maintain a Dyson sphere, including the materials needed and the energy management systems involved. Furthermore, the study of exoplanets has opened new avenues for investigating potential megastructures. A 2019 paper published in the journal Nature Astronomy discussed the potential for detecting artificial light emissions from orbiting structures around distant stars, which could indicate the presence of intelligent life. This research outlined methods for distinguishing these signals from natural astrophysical phenomena, highlighting the importance of advanced telescopes and observational techniques that could one day help us identify signs of alien technological activity. In addition to theoretical papers, observational studies have also contributed to this field. For instance, a research project led by the Breakthrough Listen initiative, which aims to scan the universe for signs of intelligent life, has systematically searched for radio signals that might suggest extraterrestrial technology. Their findings, presented in various reports, focus on the idea that if advanced civilizations exist, they may emit detectable signals, potentially as a byproduct of their energy consumption or communication method. The ongoing interest in alien megastructures has also led to discussions in popular science forums and conferences where researchers gather to share ideas and findings, exploring everything from the implications of finding such structures to the ethical considerations of contacting potential media publicity. And they argue that the public role in shaping scientific research, especially in areas related to the environment, wildlife, and conservation. When the public shows a strong interest in a particular topic, such as the health of rainforests or the status of endangered species, scientists often find themselves influenced to focus their research efforts on those issues. As funding agencies, governments, and private organizations tend to allocate resources toward projects that capture the public's attention. For instance, when a charismatic species like the orangutan or the polar bear becomes the face of a conservation campaign, researchers may receive more grants and support to study these animals, their habitats, and the impacts of climate change on their survival. Moreover, media coverage, whether through documentaries, news articles, or social media campaigns, can amplify these interests, bringing environmental issues to the forefront of public consciousness. When an environmental crisis, such as deforestation or pollution, is reported widely, it can lead to heightened public concern and demand for action, prompting scientists to focus on finding solutions or conducting research that addresses these urgent problems. This dynamic can create a feedback loop where increased media attention leads to more public engagement, which in turn influences funding and research priorities. In addition, when research findings are shared through popular media, they can spark widespread discussion and debate, sometimes leading to policy changes or new regulations aimed at protecting the environment. For example, the reporting on the effects of plastic pollution in oceans has led to significant legislative efforts aimed at reducing plastic production and improving recycling efforts. This shows how scientific research, when paired with effective media storytelling, can translate into real-world impacts and changes in public policy. Furthermore, the way scientific research is communicated to the public can also influence its reception and the willingness of people to participate in conservation efforts. If researchers can convey their findings in relatable and engaging ways through visuals or storytelling, it can enhance public understanding and foster a sense of responsibility toward nature. On the other hand, if the media coverage is overly sensational or misleading, it can create confusion or skepticism about scientific findings, potentially undermining conservation efforts. The collaboration between scientists and journalists is crucial in this context, as it allows for the accurate dissemination of scientific information while also capturing the public's imagination and interest. Engaging the public through citizen science projects, where individuals can participate in data collection and contribute to research, is another way that public interest can directly influence scientific studies. This approach not only fosters a greater appreciation for nature, but also empowers. As we delve into the fascinating realm of astronomy, the quest for understanding alien megastructures sparks the imagination and promises to reshape our approach to the cosmos, with future technologies paving the way for groundbreaking discoveries. One of the most promising advancements on the horizon is the development of next-generation telescopes, which are being designed to have unprecedented sensitivity and resolution. These telescopes, like the upcoming James Webb Space Telescope, will allow astronomers to observe distant stars and their surrounding environments in ways that were previously unimaginable, enabling the detection of even the faintest signals that might indicate the presence of artificial constructions, such as Dyson spheres or other massive structures. Additionally, the integration of adaptive optics, a technology that corrects distortions caused by Earth's atmosphere, will enhance the clarity of the images captured by these telescopes, providing a clearer view of distant celestial bodies. Moreover, the use of radio telescopes, particularly in arrays like the Square Kilometre Array, could revolutionize our ability to listen for signals that could be emitted by advanced civilizations. These arrays will combine the power of thousands of antennas, allowing scientists to scan a wider portion of the sky while also increasing the sensitivity to faint radio waves that could indicate purposeful transmissions from alien megastructures. With advancements in machine learning and artificial intelligence, the analysis of the vast amounts of data collected by these telescopes could also become more efficient, allowing for the identification of unusual patterns or signals that may warrant further investigation. On the horizon, the potential for space-based observatories is also promising. By positioning telescopes beyond our atmosphere, we can eliminate the interference of atmospheric conditions and light pollution, which often hinder our observations from Earth. Projects like the Habitable Exoplanet Observatory and others aim to explore the atmospheres of distant exoplanets, searching for biosignatures or signs of technological activity. Such missions could provide critical insights into the types of megastructures that might exist around distant stars, revealing not just their presence, but also the environments in which they thrive. In tandem with these observational advancements, the development of innovative materials and engineering techniques may enable the creation of spacecraft capable of traveling to these distant locations at unprecedented speeds. Concepts like laser propulsion and solar sails could one day allow us to reach stars within a human lifetime, opening up opportunities for in-sight exploration of any megastructures we might detect, thus providing direct evidence of their existence. Furthermore, our understanding of the potential signals that could be emitted by interdependence. In the quest for megastructures, scientists walk a fine line, balancing skepticism and open-mindedness, both of which are essential for advancing our understanding of the universe. This balance is crucial because while skepticism encourages critical thinking and rigorous questioning of extraordinary claims, open-mindedness allows for the exploration of new and unconventional ideas, which can lead to groundbreaking discoveries. When astronomers, for instance, observe unusual signals or patterns in space, they begin with a healthy dose of skepticism. They analyze the data meticulously, looking for errors, natural explanations, or even human-made interferences that could account for the observations. This careful analysis helps to ensure that any conclusions drawn are supported by robust evidence. However, if scientists were to dismiss all unusual findings outright, they might miss significant breakthroughs. Open-mindedness plays a pivotal role here, as scientists must remain receptive to the possibility that what they are observing could be something entirely new, perhaps even indicative of advanced extraterrestrial civilizations constructing massive structures in space. This idea, while speculative, has led to initiatives like the Search for Extraterrestrial Intelligence, or SETI, where researchers examine signals from space for signs of intelligent life. In this context, the balance between skepticism and open-mindedness is not merely a philosophical stance, but a practical framework guiding researchers through the complexities of the universe. Moreover, the scientific method itself embodies this balance. When formulating hypotheses about potential megastructures, scientists generate predictions based on existing knowledge, then seek out evidence to confirm or refute those predictions. This iterative process allows for adjustments based on new data, enabling a fluid approach to understanding. For example, the recent interest in the unusual light patterns from the star KIC 8,461,852, famously known as Tabby's star, illustrates how scientists can remain skeptical yet open-minded. Initially perceived as a potential indicator of an alien megastructure, further investigation revealed that the light fluctuations could also be attributed to dust clouds or other natural phenomena. Yet the very act of exploring that initial hypothesis sparked a wealth of research and discussions about what constitutes a megastructure and how we might identify one. In addition to individual researchers, collaboration within the scientific community fosters this balance. When scientists share their findings and methodologies, they engage in a dialogue that encourages both skepticism and open-mindedness. Peer review, for example, serves as a critical mechanism where other experts challenge findings and interpretations, ensuring that claims about megastructures are rigorously examined before being accepted. This collaborative depth of knowledge The ongoing research into the possibility of detecting alien megastructures has captured the imagination of scientists and the public alike. As astronomers continue to explore the cosmos for signs of advanced extraterrestrial civilizations, the next steps in this fascinating field involve a combination of advanced technologies, innovative observational strategies, and a thorough examination of existing data. One of the most promising avenues includes utilizing powerful telescopes like the James Webb Space Telescope, which can observe distant exoplanets and their surrounding environments with unprecedented detail. Researchers are particularly interested in studying unusual dimming patterns of stars, such as those seen in the case of KIC 8,462,852, often referred to as Tabby's star, where the light curve suggested the presence of large structures that could potentially be constructed by an advanced civilization. Scientists are also developing new algorithms and machine learning techniques to sift through massive data sets, looking for irregularities that might indicate artificial structures. By analyzing light curves, spectra, and other astronomical data, these methods can help identify anomalies that warrant further investigation. In addition, collaborations between various observatories and research institutions are becoming increasingly important, allowing for the sharing of data and resources. This collaborative approach enhances the ability to monitor and study specific stars over extended periods, increasing the chances of detecting fleeting or subtle signs of megastructures. Moreover, researchers are exploring the theoretical frameworks that might explain the engineering capabilities of hypothetical alien civilizations. For instance, the concept of Dyson spheres, which are structures that could encompass a star to capture its energy output, is being examined in more depth. Theoretical physicists are modeling how such structures could appear to us, considering factors like the materials required, the energy needs of a civilization, and the potential for such constructions to produce detectable signatures in the light they reflect or block. Another exciting development is the potential for interstellar probes, which could one day be sent to nearby star systems to gather direct evidence of alien technology. Initiatives like the Breakthrough Starshot project aimed to develop spacecraft capable of reaching the nearest stars within a generation. Although this technology is still in its infancy, the idea of sending probes to investigate nearby exoplanets or stars is a tantalizing prospect for future researchers. As researchers continue to investigate potential alien megastructures, they are also mindful of the need for rigorous scientific protocols. The scientific community emphasizes the importance of not jumping to conclusions based solely on anomalous data. Instead, theories must be tested, peer-reviewed, and substantiated with further observations before being accepted. The search for alien megastructures, a term that refers to hypothetical large-scale constructions built by advanced extraterrestrial civilizations, has captivated scientists and enthusiasts alike, sparking imaginations and debates about our place in the universe. The concept of megastructures first gained attention in the 1960s, when physicist Freeman Dyson proposed what is now known as the Dyson sphere, a structure that could encompass a star to capture its energy output, allowing a civilization to thrive on a colossal scale. This idea was revolutionary, as it suggested that there might be civilizations far more advanced than ours, capable of engineering monumental projects that could be detectable from Earth. Over the years, various observational techniques have been developed to search for signs of such megastructures, with astronomers employing both optical and radio telescopes to monitor star systems for unusual patterns of light or energy emissions. One of the most famous instances occurred in 2015 when astronomers detected an unusual dimming of light from the star KIC 8,462,852, leading to speculation that it could be surrounded by an alien megastructure. Although further investigations revealed it was likely due to natural phenomena such as dust or a swarm of comets. The search for these structures not only challenges our understanding of technology and energy consumption, but also raises profound theoretical implications regarding the existence of life beyond Earth. If we were to discover such structures, it could mean that we are not alone, prompting a reevaluation of our assumptions about intelligence and civilization in the cosmos. However, the quest to find alien megastructures also carries ethical considerations, as it raises questions about how we would interact with potential extraterrestrial civilizations. Should we attempt to make contact, or would it be wiser to observe them from a distance, ensuring we do not disrupt their existence or inadvertently provoke hostility? As we continue to explore the universe, the pursuit of knowledge about alien megastructures remains a fascinating intersection of science, philosophy, and ethics, inviting us to ponder the possibilities of what lies beyond our own planet and how we might engage with the broader cosmos, where the unknown still holds many mysteries waiting to be uncovered.